So in section 2, we're going to take a look at linear regression. So we're going to expand on section 1, actually talk about how to calculate the correlation coefficient, and then calculate the line of best fit for a set of data. So just to recall some of the important things we discussed in section 1. So if we think that a variable x may explain or even cause changes in another variable y, we call x an explanatory variable. And y a response variable. Okay. We used a scatter plot to display the relationship between two quantitative variables measured on the same individuals. In examining a scatter plot, we look for an overall pattern showing the form, direction, and strength of the relationship, and then we look for outliers or other deviations from the pattern. So that's a nice review of section 1. So let's start with an example, a multiple choice question. Which of the following statements about correlation is true? So a correlation of 0.2 means that 20% of the points are highly correlated. And that is not true. Correlation coefficient describes the strength or weakness between two variables. It's not a percentage. Perfect correlation, that is when the points lie exactly on a straight line, results in r equals 0, which is also not true. A perfect correlation is going to be r equals 1. That's your perfect linear equation. We're not going to see those, but that's what a perfect one would be. Correlation is not affected by which variable is called x and which is called y. That is true. It doesn't matter which variable you call the x and which one you call the y, because in the formula for calculating correlation, you end up multiplying the difference over the standard deviation by each other. So because it's multiplication, it doesn't matter which comes first. We're going to continue on and discuss why the next two are incorrect. D, correlation is not affected by extreme values, which we know is false, because in the calculation of correlation, it involves mean and standard deviation, which are both affected by outliers or extreme values. So correlation would be as well. A correlation of 0.75 indicates a relationship that is 3 times as linear as one for which the correlation is only 0.25. Also not true. It's not 3 times as linear. It just means that the relationship is stronger. There's a higher correlation between those. It does not mean it's 3 times as linear. So our correct statement was C. So let's talk about our line of best fit, which is called the least squares regression line. So least squares regression, linear regression, line of best fit, all mean the same thing. It allows you to fit a line to a scatter plot in order to be able to interpret the relationship between two variables better, as well as make predictions about the response variable. So it's called the line of best fit, linear regression line, or least squares regression line, which is going to be abbreviated LSRL. And it has an equation in a form that should look very familiar. So the equation is y hat equals ax plus b, which should look very familiar to the equation we use for slope-intercept form, which is y equals mx plus b. So very, very similar. So y hat is our predicted y value. Our explanatory variable is x. Our slope is represented by the variable a, and then our y-intercept b. All right, so this is the most common way to see it, and it is the way that we will be looking at it. There is a second least squares regression line, and that is y hat equals a plus bx. So the only difference, it is in the calculator as well, so I wanted to go over it, is it switches which variable represents the slope. So instead of a representing the slope, they change it to b. And we will not be using this equation in our calculator. We will be working off of the ax plus b one. But it is a different formula. So let's talk about how the least squares regression formula is found. So the way the line is fitted to the data is through the process method of least squares. So the main idea behind the method is that the square of the vertical distance between each data point and the line is minimized. So like you find the distance between each point and this line. And you would, because that distance could be negative if it's below the line and then positive if it's above, that distance is then squared so that we can then make sure it's positive. Just like with standard deviation, where we could subtract from the mean and we could get a positive or a negative number, which we squared so that we were looking at a positive distance. So for the slope of your regression line is important because it gives us a change of y with respect to x. So in terms of least squares regressions, it gives us the amount of change in y when x increases by 1 specifically. The intercept is also important, but only when x can actually take values close to 0. So depending on the situation, having a x value of 0 doesn't make sense. So the y-intercept is a y value we wouldn't expect, but when it does make sense, it would be expected. You can also sometimes get a y-intercept that's negative, and if your data doesn't take on negative values, the y-intercept would not make sense. So we can calculate a least squares regression line by hand or with technology, and I'm going to go over both. And I'm going to go through the steps of how you do it by hand, and then we'll talk about how to use the calculator. So for example, many schools require teachers to have evaluations done by students. A study investigated the extent to which student evaluations are related to grades. Teacher evaluations and grades are both given on a scale of 100. The results for Mrs. H for 10 of her students are given below, together with the average for each student, X. So we want to create the line that best fits this data. So we have the student grade is our X value. And then their evaluation score is the Y, because you would expect that the higher grade you have, the higher evaluation you have that teacher, because you're doing better in that class. So we're going to go through the steps to calculate it by hand, and we are going to be using our calculator quite a lot to help us with this, because again, we're not going to calculate a lot of these by hand. So the first step is to go into your list in your calculator and enter the X values into list 1 and the Y values into list 2. And you want to double check that as you're entering the values, you are entering them correctly. Because if you make a mistake, it can heavily influence the results. Another important thing for when you're entering your lists in your calculator is they both have to be the same size. You can't have one list that has more or less numbers than another, because then the calculator won't do what we need it to do. So after you have them both, we want to calculate the slope. So we need 3 things. We actually need our correlation coefficient R, and we need the standard deviation for both values. Okay. So there's two different places. So the first thing I need you to do is actually go into your mode, which is right next to the second button, and scroll all the way to the bottom and make sure your stat diagnostics are on. That's going to be really important. After that, first thing we're going to find are our standard deviations. So you're going to go into stat, you're going to go over to calc, and you're actually going to select two variable stats. That way we can get the standard deviation for both. So the first one we want is our standard deviation for our y, and this is a sample standard deviation, and it ends up being 24.25. Then our standard deviation for x, again sample, which is 16.38. In order to get our r value, we're going to go back into stat and over to calc, and then we want linreg with the ax plus b specifically, which should be right below your two variable stats. Okay. So you're going to get a few things here. You're going to get the formula y equals ax plus b. You're going to get an a value, which we'll talk about later. You'll get a b value. You'll get r squared, which is again something we're going to talk about later. The very bottom should be your r value, which is your correlation, which in this case is 0.904. So now we can do the math to calculate our slope A. So E equals our r, 0.904, times the standard deviation of y, 24.25, divided by the standard deviation of x, 16.38. And we should end up with 1.34. So just like with a regular line, your slope can be positive, it can be negative, it can be any number really. But the sign of your slope is directly related to whatever the sign of your correlation coefficient r is. So if r is positive, your slope is positive. If r is negative, your slope is negative. Because standard deviation is distance. So the standard deviations are always going to be positive. So like I said, we're not going to have to calculate r by hand, so you're just going to get it from your calculator. It also, when we calculate r, so this is where I'm coming back to that a, it does give you a when you find r. And this is a great way to check that RA that we calculated by hand matches the one the calculator gave us. And they're not going to be exact because standard deviations are rounded, but if you look, they're pretty close to at least 3 decimal places. They're exactly the same, and then they're pretty similar after that. So for us, having to 3 decimals be the same is the important part, which is why I went at least 2 decimal places for the standard deviation. And in this case, I went 3 for the correlation, just so that it was a tad bit more accurate. You can go more decimal places for the standard deviation if you want to be more accurate. It's totally up to you. Okay. The next thing we need to do is find the y-intercept. So the y-intercept is calculated by taking the mean of your y data set minus the slope we just calculated times the mean of our x data. So I'm going to copy our slope down that we just calculated, 1.34. And we're going to go back into that 2 variable stats, and now we're going to write down the mean of our x data and the mean of our y. So the mean of x was 72.4, and the mean for y was 67.6. So the b, which is our y-intercept, equals 67.6 minus our slope 1.34 times 72.4. Which gives us negative 29.42. And if we check with our linreg, This one is a little bit more off because the standard deviation was rounded a lot more. So the calculator gives us B as negative 29.31, and we have negative 29.42, which is acceptable. If we had taken our slope to more decimal places, our y-intercept would have been closer to what the calculator gave us, but I only require 2 decimals for slope. If you wanted to go more, you could. So just a couple information, your least squares regression line is actually always going to pass through the point of where the means for both of your data are. So like if I had the point 67.6 comma 72.4, my line of best fit is going to pass through that point, which is why we use it to calculate the y-intercept. So now that we have the slope and the y-intercept, we can write our equation. So y hat equals 1.34x minus 29.42. And now that we have this equation, we can use it to predict values that aren't in our data set. We can also use it to predict values that are in our data set to determine how close our equation is. So we're going to use the equation to predict what evaluation Ms. Huffman will get from a student who scored an 81. So 81 is our x. So we'll have y hat equals 1.34 times 81 minus 29.42. And we get that they gave me a score of 79.12. Okay. Next, we want to interpret the slope in the context of the problem. So remember, slope is the change in y over the change in x. So with a slope of 1.34, it tells us that Ms. Huffman's evaluation scores increase by 1.34 for every increase of 1 in for a student's grade. Okay. It is important to be able to interpret the slope in context of whatever your example may be. That way you're actually understanding if that slope makes sense, what that slope means. So in this case, we're looking at how an evaluation score changes based on how your grade changes. So as your grade increases by 1, so as a student's grade increases by 1 point, my evaluation scores are going to increase by 1.34. Okay. Do you think that students' grades and evaluation students give their teachers are related? Explain. So there's a couple things we could use in our explanation here. We can use our correlation coefficient R, or we can use our data. So I'm going to do both. So in both cases, we're going to go with yes. All right. So one reason could be because R equals 0.904, and this indicates a strong positive relationship. Okay, that's one way, that's one thing we can use. We can use the correlation coefficient since it describes strength and direction. So because this is positive and it's a pretty strong value, we could say yes. The second reason, we can use values we plug in and compare them to the actual data. So we don't have a score of 80 or 81 or 82. So the closest score we have in our data set is an 85. So we could say yes, because a student with a score of 81 gave an evaluation of, sorry, not 81, 85. And they gave it an evaluation of 80, which is similar to what we get if we use our least squares regression line. So like if I were to use my least square regression line and use the 85, right? 1.34 times 85 and then minus 29.42, we get 84.5. Which is similar / close to what we got. The better one is the first one. So it is better to use the correlation coefficient in your reasoning. It's not mandatory, but it is a little bit better of a reasoning than using our actual equation. Okay, so we've already talked about how to calculate your least squares regression line on the calculator. Once you have your data in your two lists, you go to stat, over to calc, and then you want number 4, which is linreg with the ax plus b. Okay. So one thing we have to worry about with our regression lines is we have to be careful of making predictions beyond what the data shows. So extrapolation, which is a very fancy word, extrapolation, let's see if I can spell it, extrapolation is the use of a regression line for a prediction far outside the interval of values of the explanatory variable x used to obtain the line. And such predictions are often not accurate. So we want to make sure that if we're going to use our least squares regression line, we're going to plug in for values for x that are in the range or within very, very close values of range. We don't want to go too far outside our range of values because it is not going to give us accurate results. So something that you may have heard before or heard me mention is the statement, correlation does not imply causation, or correlation does not mean causation. So this is a very important statement in statistics. So there was a study done that showed a strong positive linear relationship between ice cream sales and homicides in New York City. Does this mean that if we stop selling ice cream, we will have no more homicides? No. It's something called a confounding variable, which we are going to talk about more in chapter 3. Those are other variables that affect your data that you're not looking at. Okay. So there are other reasons why ice cream sales and homicides in New York City increase during the summer. It doesn't mean that selling ice cream causes more murders. One thing, it's a lot hotter in the summer, so ice cream is sold a lot more. Also could be a variable that affects homicides, because if it's hotter, people are angrier, they may not have AC, so they're more prone to maybe commit armed robbery. So there's a lot of other things that could have an effect on the ice cream sales and homicides in New York City. So correlation does not mean causation. Does not mean that one variable causes the other just because they have a strong correlation. Very important statement. There's also something called the coefficient of determination. So the strength of a prediction that uses your least squares regression line depends on how close the data points are to the regression line. And the mathematical approach to describing the strength is called the coefficient of determination. And when we looked at the LINREG, that R squared value is the coefficient of determination. So it gives us the proportion of variation in the values of y that is explained by the least squares regression of y on x. And it happens to be the square of the correlation coefficient. So in the example we just did, R was 0.904. So our coefficient of determination, R squared, is 0.904 squared. Which is 0.817. Okay? So whenever we're using our regression line for prediction, we're also going to take a look at R squared to measure how successful the regression is in explaining the response. Now, if we used 0.9, which is I think what was originally used in the notes, or even farther, R squared is 0.818. It just has to do with rounding. So that would mean 81.8% of the variation in teacher evaluations, which is our dependent variable, can be explained by the linear relationship it has with the student class average, which is the independent variable. So a higher R squared is better than a lower R squared. And also, the stronger the relationship, the larger R squared is going to be. That also brings us to something called residuals. So in the majority of cases, a least squares regression is not going to pass exactly through all of the points. Okay? So even if we use that line to make predictions about our dependent variable, there's still going to be some error from the actual y value. And we saw that in the example where I used the equation to calculate our value for a score of 85. It was different from the actual y value. So because we used the line to predict y from x, the prediction errors we make are errors in y, which is the vertical direction in the scatter plot. So a good regression makes the vertical deviations of the points from the line as small as possible. So that method of least square regression that I talked about, you want those distances from the point to the line vertically to be very small. That way you have the best line. So the residual is the distance between an observed value of the response variable and the value predicted by the regression line. So the formula for a residual equals observed minus predicted, or if we're going to look at it mathematically, it equals your actual y value minus y hat. So if the residual is positive, the observed point lies above the least squares regression line. And if the residual is negative, it lies below the least squares regression line. Right? And if we add up all of the residuals from the data, we will get 0. Because that's why using a least squares residual involves squaring them, then adding them up. Because they all end up being the same distance once you add them all together. So let's take a look at an example and use residuals. So everyone knows that cars and trucks lose value the more they are driven. So can we predict the price of a used Ford F-150 Super Crew 4x4 if we know how many miles it has on the odometer? A random sample of 16 used trucks was selected from autotrader.com, and here's a graph. So we have their miles driven on the x-axis, which is our explanatory variable. And we have their price in dollars on our y-axis, which is our response. And as we see, as your miles driven increases, your price decreases, which makes more sense. The more miles a car has, the less money it will sell for. And we already have our least squares regression. So y equals negative 0.1629x plus 38,257. So and this is one of those cases where a y-intercept doesn't make sense. So you're saying a used car with 0 miles would cost $38,257. And there's no such thing as a used car with 0 miles. Then it would be a new car. So here a y-intercept doesn't really make sense. So we're going to find and interpret the residual for the Ford F-150 that had 70,583 miles driven and its price of $21,994. So we're going to use our x, 70,583, get out our y hat, and determine what the residual is for the actual price it sold. So we're going to have negative 0.1629 times the 70,583 plus 38,257. And we're going to get a y hat of 26,759.03. So remember, this is a price, which means we have to have 2 decimal places. All right, next we're going to calculate our residual, which is y minus y hat. So it's the actual minus the predicted. So our actual price was $21,994 minus our predicted $26,759.03, which is going to give us a residual of negative $47,65.03. So our residual would be below the least squares regression line because it is a negative value. So our equation tells us that the car should be worth more money than it actually is. So what we end up doing is plotting all of our residuals to determine if the linear regression equation we have is a good fit for the data we have. So we plot our residuals against the explanatory variable. So our explanatory variable in this case is miles driven. Like I said, it helps us to assess whether a linear model is appropriate. So in this truck example, if we calculated the residuals for each point, our miles driven would be the x-axis, and our residual, the way we plot them, is 0 is always in the middle, and then we have to go up in the positive direction by the same amount and down in the negative direction by the same amount, and they have to end at the same value. That is very important for residuals. So when we actually look at the graph of residuals, the 0 ends up being our regression line. That's where, they'd all basically fall on it. And they magnify the deviation of points from a line. They tell you how far your equation actually was from what you looked at. And it makes it easier to see an unusual pattern, so it helps to determine if a linear model is an appropriate one. So when an obvious curved pattern exists in a residual plot, the model we are using is not appropriate. So basically, when you graph residuals, you want the points to fall in random places. And if they didn't, that would be bad. So for example, we could have curved. Okay, so and it doesn't matter what x and y are. So we have our residual. If we had a bunch of residuals that ended up looking curved, like a parabola in the positive or negative, it could be opening down as well, that would tell us a linear model is not a great fit for the data. You can also get something called fanning. So when that happens, they kind of start close to the line and then they start to spread out, creating what looks like a fan. So both of these involve a curved pattern of some sort. So the model we're using is not appropriate. So if we look at the residual plot on the previous page, the points do not follow an obvious pattern, which means the model we're using is appropriate, which is weird to think about. You would think if it were a linear equation, you would want the residuals to form some type of line, but we actually want them to be more spread out and not have a pattern when we graph them. So when it comes to doing residual plots on the calculator, there is no residual graph. So the process is a little bit different. So we can get our residuals when we perform linreg. So they're stored in a list called res_id, which is found in the list menu. So every time you perform a new regression, a new set of residuals is stored. So to get that, you have to enter your data into list 1 and list 2 and actually calculate linreg. And then you're gonna so you have to do something special to get it in the stat plot. So again, you wanna make sure stat plot is on, and you're gonna choose and then when you go to Y list, you need to clear out list 2 and you're going to hit second stat, and then you're going to go all the way down on to RESID, and then you'll hit zoom 9 like normal. Let me know if you have any questions about calculating lines of best fit, interpreting standard correlation coefficient, or residuals.